Sunil? Sunil or Satish? Hello?
Hello. Yeah, thank you. This works. Hey, anybody to join in this seminar? Any non-samosa people here? Yeah. Come enjoy. Yeah. All right.
Yeah, you can just say that you are ready to start.
Yeah. Okay. Sure. Absolutely. Yeah. Hey, so it's a pleasure to introduce Professor PCD. You all know him. Yeah. So hello, sir. Nice to see you. Yeah. After a while. Yeah.
How are you, Raghu?
I'm
Wonderful.
good, so, yeah, I need to respond to your email, but we'll do that soon. Yeah. So nice.
Yes.
Yeah. So the floor is yours.
We have a lot to catch up with, and
pleasure. Yeah.
If we are ready to begin the session, are we?
We are. Yeah. We can start the session. Yeah.
Excellent. So good afternoon, everybody, and we have assembled for another exciting talk today. We had Arvinda's talk just a few days ago, and it is a matter of great pride and privilege for me that we have Ranjan Modak today, and Ranjan and Arvinda have collaborated also, in recent times. So it is really marvelous to see their work coming together. It is a very rare situation, I must say, that two young faculty members join a new institute and enter a collaboration and publish absolutely top quality work. In fact, after Arvinda's talk a few days ago, I felt that there is so much to learn from this, and I'm sure it is going to be the same with Ranjan's talk. So looking forward to this talk. And we have with us Dr. Raghunath from ICER Tirupati, the quantum chemist, and he will introduce our speaker today, Dr. Ranjan Modak, and conduct the session. Raghu?
Sure. Thanks a lot, sir. Thanks a lot for passing on. So it's a pleasure, to have. It's more or less a continuation from Dr. Aravinda's talk on Friday. Yeah, Thursday. Sorry. Yeah. So Dr. Ranjan Modak is a collaborator of Dr. Aravinda, and I look forward to inviting him. So he is here with us. He finished his BSc in physics from Jadavpur University.
Essentially, all of us like IIT Tirupati.
Got you. Okay. Yeah. So he's saying it's okay. Basically, he's not enough of him. So that we can right away, introduce Professor Modak. Yeah, absolutely. So, no ICER fellow here?
There are.
I think at least a brief introduction is desirable. The reason is This is going to stay on the YouTube, and there may be some others from other institutions
would want to know it, right?
who may
Anyways,
get, yeah.
So Modak's work is in, a very condensed form of condensed matter physics. So yeah, very. So therefore, like it's an absolute pleasure to. It's much more common to see people working on equilibrium many body physics, but then like non-equilibrium many body physics is pretty rare, and he's one of those experts in it. So atop this, like he's also working on DMRG, which is again a very cool topic, and it's an absolute pleasure to have him. He finished his BSc from Jadavpur University as he started, yeah, and then he finished his master's from IIT Kharagpur, yeah, in 2010, yeah. And this was, of course, followed by his PhD from IISc Bangalore, as you all know. And now, what did he do his postdoc? Pop quiz. No student knows that. What did you do your postdoc? Sorry? Yeah, but what about you, the students, right? Yeah. You should be following it up, right? Anyway, so he did his postdoc from Penn State, right? And he's here with us, and he obtained his, he did a great job, like in a collaborative work with Dr. Aravinda, and I hand the podium over to him, so really look forward to your talk. Although, I must also say one thing on account of the, the seminar, despite this being a stellar seminar, I mean, I have to, I cannot violate the Heisenberg's uncertainty principle. I have a class, in the neighboring room. So I'll introduce the speaker and then I'll get back to my class. Okay. Yeah. So on that note, sir, yeah.
But then who will remind me that I have to?
I will come back.
Oh, you will come.
I will come back. Yeah.
That I need to shut up.
Absolutely. Yeah. Just like you said it now to me.
Yeah.
Thanks a lot. Okay. I'll get going. Okay.
Yeah. Thanks. So, can you give me the Am I audible? Right? Hello? Yeah. Okay.
Hello, I'm not able to hear anything. Everyone was audible until now, and now for the last minute or
sorry.
so.
Yeah.
Okay.
Just. Okay. Am I audible now?
Yes. All right. Thank you.
Yeah. Okay. So let's begin. So first of all, you can see there is a bit of change in the title, right? So whatever was in the abstract, it's not there. So so my initial idea was to talk about this particular work with Aravinda regarding complexity growth in free harmonic system. Then I thought that, okay, let's talk about this three kind of concepts. And the idea of the talk will be, at the end of the day, if you go back and read this paper, then you will understand the paper. Okay. So I just want to kind of introduce these three concepts, and let's see how it goes. Okay. And just tell me 5 minutes before when I have to start. Okay. 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 So it's not changing. No, it's still not working. Next slide, it's not. Okay. Okay. Yeah. So the first question which I'm trying to address here is that what exactly we mean thermalization of isolated quantum system, right? So the first question is that what is an isolated system? Now, an isolated system, you can think that I have a this system and which is not interacting with the surrounding, right? So there is change either heat or matter with the outside. And in other words, there is no interaction with the surrounding, right? So the question is that how you define thermalization in such system, because when we read this, let's say, Patria book or statistical mechanics book, we essentially assume that, okay, there is some infinite bath which has some temperature and you bring your system in contact with the bath and the system gets thermalized and it has that same temperature. Now, if you don't have any interaction with the surrounding, then you cannot talk about all those things, right? Because there is nothing like an infinite bath which is essentially thermalizing your whole system. Now, in this kind of stuff, the idea is, it's actually not working properly. Yeah, I need to. So shall I be here or something? Yeah, I think. Okay. So yeah. So let's say this is my whole system, and that system is described by some Hamiltonian H, and I prepare my initial state to be some size, right? And what I really want to do, I want to do some, I want to define some observable OA which act in this small part of this big system. By the way, this big system is now isolated, so it's completely isolated. So in a big system, I have a small subsystem, if you like, and this observable is acting on this subsystem, and the whole system is actually governed by this Hamiltonian H, and initial state is psi naught, which is a pure state. So this is essentially the setup. Now, of course, this is the time evolved state. It is nothing but e to the power minus t by psi naught. Now the question is that now I can calculate this reduced density matrix, which is nothing but you have the whole density matrix, which is now depends on temperature time. Now I trace over the B of the system. I get a reduced density matrix, which is nothing but this guy. Now in the long time limit, if this quantity rho at is given by some thermal density matrix, which we all know, it's just the canonical density matrix we all encountered in our Patria book or any statistical mechanics book. So if this satisfies, then we say this isolated system has thermalized. And of course, I mean, the usual statistical sense, then if you calculate the expectation value in the long time limit, you will see that this is nothing but the space of this rho thermal and OA, right? So this is what usually one can expect if you have some isolated system. And this is mostly this is, I mean, people used to believe that this is how an isolated system will thermalize itself. So in some sense, you can think that it's acting as its own bath, right? The system is acting as its own bath. So you have the whole system, you look at some small subsystem of it, and the rest of the system is essentially acting as a bath and making the subsystem thermalized. And it does not matter. You can take some small subsystem here, it will follow the same thing. Okay. So it's the setup is clear, right? And okay, so feel free to interrupt me in between. So I don't have any agenda. So even if you are not able to the talk, it's completely fine. So yeah. Okay. So now the story becomes interesting. So in last 20 years or so, there has been a lot of experiment in cold atom setup where you can really prepare the system in kind of very low temperature. So you can actually prepare the isolated system if you like. Now, there are many experiments. So I will just focus on this particular experiment because this was done in Penn State, actually in David Weiss's lab. So they call it Newton-Cardell experiment, quantum Newton-Cardell. So here is the kind of the setup nicely. So you have some a lattice system where you have some fermion and you prepare the system in some trap, some harmonic trap. So what will happen? So particle will be kind of localized in the minima of the trap, right? Then you suddenly switch off the trap. Okay. And then what will happen? This particle will start move around, and it's kind of a closed setup. So it will go to the boundary, reflect back, and do this kind of to and fro motion. And the idea is that after a certain time, things will be thermalized the way I described earlier, like take the whole system, subsystem, and so on and so forth. And you expect that some long time expectation value can be explained by those thermal density matrix. So that was the naive expectation, if you like. But what these people found was quite amazing. So they come to some momentum distribution. It's quite irrelevant for the talk. But the most interesting part is here is, so this is the experimental data, the solid line or the red line, if you like. So they have smoothened up it. And this dash line or this dash line is essentially the thermal prediction. So if system has thermalized the way the previous slide, if you do that, then you get this dash line. But you see they are off. They don't match. Then the question begins that what is happening in this kind of system? So what is happening, because in the sense that it's not obeying the usual thermalization notion which a priori will have, right? So that's essentially so essentially whatever I'm going to talk later is essentially motivated by all these experiments. So the experiment came first, and then people try to understand that what is actually happening in such system. Yeah. So that was kind of belief. Yeah, but still it will never match. Kind of, yeah. I forgot the detail, but yeah, kind of. Okay, good. So now the belief is that the system they are looking at, they are not actually the usual thermal system. They are actually integrable system. So let me now spend a couple of minutes defining what is integrability. Of course, defining in the physicist sense, not as a mathematical, I mean, not too much rigorous mathematics I will do, but okay. So classically, what we know that if you have, let's say, n degrees of freedom, and so basically you have, let's say, 2n dimensional phase space, then this n independent integrals of motion will have this nice Poisson bracket relation. So you have this I, which are, let's say, Poisson commute with each other and also Poisson commute with the Hamilton. And you have n of them. And here n is nothing but the degrees of freedom of your problem. Or in other words, you actually so you can actually do an action angle variable calculation, and you can get the solution for this particular Hamilton. Now, if you think a bit, any energy conserving one-dimensional system essentially integrable in this particular way, because you see you need one, because degrees of freedom is I mean you need 1 degree, so it's a 1 degrees of freedom system, and energy is a conserved quantity, right? So it will kind of obeys this particular setup, and essentially we can say that okay, this is integrable, and it is indeed any 1D system, 1D energy conserving system, classical system is actually integrable. Now things get slightly interesting if you look into the 2D system. So this is nothing but a 2-dimensional harmonic oscillator, right? So you have this Q, P1 squared, Q1 squared, P2 squared, Q2 squared. And here you can also construct two conserved charges, I1, I2. And you can check that they Poisson commute with each other and also Poisson commute with the Hamiltonian. So it's also an integrable, classical integrable system. Okay, I should emphasize that you can construct these conserved charges different way, but they has to be functionally independent. What I mean that you can add them and you can subtract them. They are also conserved charge, but they are not functionally independent, given that I already have I1 and I2. So that's important. Okay. So now this is again an example of integrable and non-integrable system. I mean the famous billiard example. So here you see that you have this nice periodic orbit, which is essentially a signature of classical integrable system. On the other hand, here you have this weird shape. So this is called a unimovic stadium. And you see that nice, not nice, chaotic trajectories. And this is essentially, you cannot have the, the formal integrability definition I had. So it does not satisfy, and it's not actually integrable, classically, of course. So this is essentially the story I wanted to tell you about the integrability and non-integrability in the context of classical system. Okay. Any questions so far? Okay. Okay. Now things get a bit non-trivial when we look into the quantum system. Why it become non-trivial? Because like previous, in this case, I could draw this nice trajectory, right? Because I can track the particles. And in this case, I cannot do that because I don't notion of phase space and other things. Right? So I should emphasize that the definition of integrable quantum system and all these things are kind of tricky. I'm just following a particular notion, and you can, it's fine for us, okay? But you can have a different definitions and so on and so forth. So let's just naively, if I kind of extrapolate this idea, whether you know quantum mechanics or not, you know that whenever you see a Poisson bracket, you just change it to the commutator, it becomes quantum mechanics, right? So we do the same thing, okay? So I have my Hamiltonian quantum, right? And now I say that I have these conserved charges which commute with each other, not Poisson commute, and they also commute with the Hamiltonian. And if I can have that many those conserved charges, then I call it a integrable system. Now you will ask the following question: what is the notion of degrees of freedom here, right? So that's why we don't integrable dimension. Mostly we talk about the integrable system in the thermodynamic limit, where actually you need infinitely many conserved charges. So when you are talking about a thermodynamic limit, you essentially kind of think that Hilbert space is infinite, so on and so forth. So you need infinitely many conserved charges which commute with each other and the commute with the Hamiltonian. So that's essentially the definition I will follow when I say the quantum integrable system. Okay. Now also one thing, whenever I have this kind of conserved quantities, the way it will be manifested in the spectrum is it will leave the degeneracy. Right? So for an example, take the hydrogen atom problem, right? I know that there is L squared, Lz, all these quantities are conserved quantities, right? So that's essentially increase the degeneracy. And that's why you see that all the quantum number does not appear in the energy. It's essentially 2n squared. It's just, energy is just 1 by n squared. There is no Lm, right? That's because you have these conserved quantities and hence you increase the degeneracy. So similarly here, even without doing anything, the naive expectation will be, if I have this infinitely many conserved quantities, increase the degeneracy in the spectrum. And now the question will be how I can characterize that. So of course, if you want to catch the degeneracy in the spectrum, the quantity you should calculate is the difference in energy, right? Because what do you expect if you have degeneracy? This quantity. So let's say you have this is energy level, right? And you compute the nearest energy gap, if you like. If you have degeneracy, then if I plot the distribution of S, it should have a peak at S is equal to 0. Because that means you have that many energy level are kind of degenerate. So there is no gap, right? What I expect is that if I plot this quantity, the successive gap of energy eigenvalues, I should get a peak at S is equal to 0. And it turns out, at least for the type of model we are interested in, is that spacing distribution is really has a peak at S is equal to 0. And it obeys this particular distribution, which is nothing but exponential minus x. Okay. So this is how, if you give me an Hamiltonian without knowing anything, what I will do, I will diagonalize the Hamiltonian, I get the energy eigenvalues, I will arrange them in this order. Okay. And then I will plot the histogram. If it is obeys this kind of distribution, then I will say, okay, this is integrable, quantum integrable system. Okay. This is the definition we will use. Now, if I talk about non-integrable system, where the definition is don't the quantities, these i's which I defined earlier, and hence you will not see any degeneracy, right? And if I don't see any degeneracy, that means this A should be, this if I plot the spacing distribution, that should goes to 0 as I approach to 0, right? So there are no two levels which are having the same energy. So we call it a label repulsion essentially. So that's the expectation. And it turns out, again, I'm not going into too much detail because I want to talk about something else, but it shows a spacing distribution which shows something of this form, which has some relation with random matrix theory and so on. So I'm not going into those details. But the way to distinguish this to integrable and non-integrable quantum model is just look at this distribution. Here it has a peak at s is equal to 0. And here at s is equal to 0, you see this guy is 0. Okay. And this is just coming because you have this conserved quantities in one case, and in other case, you don't have conserved quantities. As simple as that. Fine. So far, so good. Okay. Okay, great. Now let's talk about some examples. So this is a very simple model. So you have this lattice point. So you think that these are lattice points. And some electrons can hop around into nearest neighbor. So this E is nothing but the hopping amplitude. And you have this hopping amplitude. So this is basically the Hamiltonian. So if you are not familiar with this thing, P dagger, it's just telling you, I guess you all have done this bosonic harmonic oscillator problem. Whenever you have A dagger, it's actually create one boson. And when you have A, that actually destroy one boson. So this is exactly the same guy, but it's not creating a boson, it's creating a fermion. And destroying one fermion. So P is destroying or annihilating one fermion, and P dagger is actually creating one fermion. And this I index is telling you at what site it's creating. That's what this particular Hamiltonian is basically telling you. Okay. And you see, it has I plus 1, so that means it will create one at particular site and destroy one in the other side. So essentially, it means you are taking one electron here and hopping it to the nearest site. That's what this Hamiltonian is doing with some amplitude or probability T. That's what. Okay. This is fine, right? Okay. So this is this Hamiltonian. One of the simplest Hamiltonian you can think about, especially in the condensed matter literature, and you call it tight binding Hamiltonian. Okay. Now this Hamiltonian, actually one can exactly solve this Hamiltonian going to the momentum space. So this is nothing but going to some Fourier basis. You have done this probably. This is discrete Fourier transformation basically. If you do that, do some algebra, you'll get that this becomes this, and this cos k is nothing but the energy level. So this is diagonal. So it's exactly solved. And you see this nk, they are actually conserved quantities. This nk commute with any other nk. Given that h I can write down as a sum of nk, this nk will also commute with the h. So this is basically this all these nks, you have infinitely many, given that thermodynamic limit. So you have infinitely many nks, which essentially the rule we had, right? You need to have this conserved quantity infinitely many. They commute with each other, commute with the Hamiltonian. That obeys here, and these nks are doing that job. So this is essentially one of the simplest example you can think of for this integrable quantum model. Okay. Okay. Kind of. Okay. Good. Okay. Okay. This is not okay. Oh, it's okay. Oh, sorry. Okay. So now let's make things a bit spicy. So I now introduce some non-trivial quantity here. Okay. So this is ni plus 1. Again, you don't need to worry too much. The only thing I want to tell you that this is not quadratic anymore. So this is basically an interaction term. So it's just nearest neighbor interaction and so on. So again, if you don't know, that's not important. The only thing I can tell you, this is slightly non-trivial quantum model, which is again integrable, but the charges, this conserved charges are not as straightforward as it was here. But again, you can construct all of them. So it is again an example of such integrable model. Okay. Okay. So now let's break the integrability. So so how I can break that? So I add this blue term. Again, now you know that this is nothing but an hopping, but next nearest neighbor, because I have I plus 2. So if I don't have blue term, I just argued, or I just told you that this is integrable. And now I add this term, it's become non-integrable. And now whatever I told you earlier, the level spacing and so on, if it is non-integrable, then it should obey something which this blue line is telling you, because this is something which has S is equal to 0 at PS. I mean, its PS is 0 as I tends to 0. I mean, when my S tends to 0. And this red dot dash line is nothing but the Poissonian, right? So I see as I increase my T prime, so 0.02, 0.05, and so on and so forth, I see a nice crossover from this Poissonian to GOE. So you see, you can detect an integrability to non-integrability transition just looking at the spacing distribution. So I just put it there just for just to emphasize what I said is kind of work. Okay. Now again, come back to the statistical mechanism. So the initial motivation, right? So so now we think that you have this kind of system where you have all these conserved charges, I alphas basically. You have infinitely many. Now the point is, if I really want to do statistical mechanics for such system, when I say statistical mechanics, I mean I want to calculate something long time limit and want to see that whether some statistical mechanics predictions can match that long time predictions and so on and so forth. So I need to, if I calculate the density matrix, I need to incorporate all these conserved charges. Previously, I had only beta h. When I was doing the usual statistical mechanics, there's the canonical statistical mechanics if you like, I had e to the power beta h. But now, given all this integrable system has all these conserved charges, I really need to incorporate all these I alphas with appropriate Lagrange multiplier. I just want to emphasize the beta, the temperature which we had, is nothing but the Lagrange multiplier for the Hamiltonian. So here I need to add this Lagrange multiplier, do this, and this Lagrange multiplier gets fixed from the initial condition. But in case of e to the power minus beta h, beta used to get fixed by the initial energy. And it's a unitary dynamic, so energy does not change. So whatever beta you need to put, it will be determined by the energy of your system. So beta kind of the Lagrange multiplier of the Hamiltonian. In this case, all these lambda alphas are the Lagrange multiplier for all the conserved quantities you have. So this ensemble, and this density matrix I need to use if I really want to understand the integrable system statistical mechanics. Good so far? It can, yeah, it can. Sorry? This is for integrable system. Exactly. Integrable system, you don't have charges, right? See. Conserved charges? No. No, you can't. I mean, in principle you can, but it's not obvious. As a matter of fact, there is again, if you take the simplest model, it's always there is a debate. I mean, what are the complete conserved charges and so on and so forth. So that debate is still going on. But yeah, I mean, technically speaking, this is what you need to do. You have to do. It's a conjecture. Actually, it's a conjecture. But for some system, you can show it. For an example, this Bethe-Ansatz system, you can show it, like the XXZ type of. Yeah. Okay. Okay. So this is just a quick numerical demonstration that it works. I take some. So by the way, it is clear that it is for integrable system, right? Because for non-integrable system, you don't have any other conserved charges. Hamiltonian is kind of the only conserved charges you have, apart from some trivial ones. But yeah. Yeah. So I take some momentum distribution, some long time calculation I'm doing for some integrable model. What I want to show here is that whatever I told you, I'm not cheating. So you see that this is blue is the exact calculation, time evolution. This red, if you can see it, I don't know, it's a GG prediction, red dash dot. And the green one is a thermal, like the usual prediction you will have if you only have H as a conserved quantity and you do some e to the power minus beta H type of stuff. Okay, so this green, they don't match, but this red dash dot, they match. So GG works. Okay, so that's just what I want to explain. Yeah, because anyway, the state in the long time limit. Okay, so now, so this is essentially my main job is done. So I can principle, I can shut up. But okay, given that I still have 10 minutes, I will talk about some other stuff. Okay. So now I want to emphasize something which is known as entanglement dynamics. Okay. And for the integrable system, that's very important. So I just want to tell you something very interesting. Even though in last two lectures, like Arvinda and Arun, so they were saying that okay, entanglement is a quantum quantity and so on and so forth. It's very difficult and so on and so forth. Of course, it is. But very strikingly or very interestingly, for integrable system, one can have a semi-classical picture to understand how an entanglement dynamic will go. Okay, so you can understand that, and it works beautifully. So okay, before that, let me just define what is entanglement. So you take this my big system, A plus B. This is my whole system. I take a subsystem A. This is this red guy. So the total state is basically a pure state. So I have this. This is a bipartite system, so I can write down HA cross HB. And if I take the von Neumann entropy for this reduced density matrix, that become my entanglement entropy. Okay, so after Arvinda's talk, you all have seen this, so I'll not spend too much time. Okay, now the question we are asking here, let's say I start with some product state. Okay, so entanglement is 0. I do some unitary evolution under some integrable Hamiltonian. So e to the power IHT, but H is some integrable Hamiltonian. Now, the system will get some entanglement. So I would expect that the entanglement will grow, right? And the question, I understand this simple thing with some classical or semi-classical picture. So that's the question. Now here is this. This is essentially at some point it was a conjecture, but for some simple model, one can show this thing exactly. So this is the idea. So now this is my whole system, let's say BAA. Okay. Think about a 1D system. This A is my subsystem. So total system, this is my subsystem. I prepare my initial state to be some product state. Then I quench it. Now, when I quench it, at each point in the space, a quasi-particle pair gets generated. Okay, so this blue line are essentially a quasi-particle pair. So you can think that some dressed particle, okay, at each point, and they just move ballistically in two directions. So let's say you can think that there are some V and they are moving with some velocity V. That's the first assumption. Not assumption, but this is the first thing. You just believe my statement. Okay. Second thing, only those quasi-particles will generate entanglement which are actually starting from the same point. So that means this blue line and this blue line, they will not carry entanglement. Only this blue line and with this blue line, they will only carry entanglement. Okay. And the third thing, at a given time, the number of quasi-particles which are at this region A and the number of quasi-particles which are at this region B, either this side or that side, they will essentially be a measure of the entanglement at that particular time. Okay, so these are the three things. Okay, let me again go back. So first point, once I quench it, at each point in the space, a quasi-particle pair generates, and they start moving ballistically with two opposite velocities. So this is basically given by this particular. No, they are just excitation. They are just excitation, and because you are quenching, so you essentially are pumping some energy in the initial state, and that is just. So they start moving. Second thing, only those quasi-particles will create entanglement, those which are essentially generated from the same point. So that means this and this, they cannot entangle. So essentially they are only this quantity and this two can kind of be an entangled pair. And the third thing, you essentially need to count at a given time. Let's say at this time, so if you look at this picture, y-axis is the time, x-axis is the space. So at this particular time, I will just see that how many quasi-particles are there, which are at this B side. I mean, when I say B, I mean this side, also that side. And I mean, how many quasi-particles are there which are in this A side? And those who are actually generated from the same point in the space, because they only carry entanglement. So if you believe in three simple concepts, then with a bit of thinking, you can essentially understand that this whole entanglement business, essentially, you can just write down with some counting problem. It's essentially become a counting problem, because essentially what you are doing is you are counting how many quasi-particles are there at a given time which are sharing A and B. And this whole entanglement entropy, you can just write down in this formula, where up to certain time t, it has some linear growth in t, and then finally it saturates. That's it. Okay, and that you can do only for integrable system, where the belief is that this stable quasi-particle exists. So, so all this quasi-particle needs to have a lifetime, and that's actually infinite. I mean, of course, when I say infinite, I think about the thermodynamic limit and so on and so forth. So only for integrable system, this quasi-particle exists and their lifetime is infinite, and hence this picture works. And this picture tells you that it has a nice linear growth and then it saturates. Okay. Now let's do, okay. So in this case, I have essentially two notions. I mean, two unknown. One is V, one is F. So V is essentially quasi-particle velocity, because I said the quasi-particle moves like this, but with some velocity. So you need velocities. And that basically can be fixed by the thermal density matrix, if you like. Given that these are integrable systems, so that gets fixed by the GG density matrix. Okay. So by the way, I just want to emphasize this V, this velocity of quasi-particle, they are not necessarily constant. They can depend on quasi-momentum and so on and so forth. As a matter of fact, they are not constant. So anyway, but naively speaking, this is what you have. And with notion of the integrability, you can have this density matrix GG, and you get this all this Sn and F lambda which are required essentially. Okay. Okay. So again, let's check whether all these things work or not. So let's look into this integrable nearest neighbor tight binding model. So it's seeing any difference, because QP quasi-particle picture and they matches. They just on top of each other. Okay. Yeah. They are ballistically moved.
Something always true, or it is a seems to be a crucial ingredient for this.
It is very crucial.
So,
yeah.
Is it always true? It's a universal fact that
it is universal. It is a universal fact for integrable system.
Okay.
Yes. Okay. So okay, that's a good point. It does not work for the long range model. So for the long range model, the quasi-particle, even if you have those quasi-particles, they don't move ballistically. So in other words, that's why if you look at the entanglement growth in long range models, they are not linear.
But is it always also the case for critical model where some long range entanglement is there but not long range?
That's a good question.
For example, random singlet.
Got it. That I cannot comment. I need to check. Yeah, that's a tricky thing. Yeah, that's right. Yeah. Okay, good. So, any question so far? How you will? No. I'm not generating. So, no. So if you point some initial state, so this is a picture. So this quasi-particle, you will not able to see it. So I mean, you can see its effect. So it's not like something which you can see, but you can understand its effect. So if you see some entanglement growth like this in some system, so and you can mimic the whole situation from this picture, then you will say, okay, probably underlying this phenomena happened, and hence I'm seeing it. So you understand. So for an example, even if you say that, okay, this is this, how you know that? So you you measure the weight and you say. So you kind of understand its effect.
It's experimentally verified.
No, the entanglement growth is experimentally verified. Now it matches with let's say this quasi-particle picture. Then you can say that, okay, the underlying mechanism must be like this. At least this is one example, one way of explaining it. That's it. Yeah. And where everything is analytic, basically. Essentially, it's a counting problem. Okay. Okay. So, okay, let me just keep all these things. So, when you have finite size system, you see a dip and so on, because quasi-practical cannot grow, cannot just away from a particular point, because finally you have a finite boundary, so it needs to come back and so on. So, for that, you see lots of stuff. So, anyways, I think I'll just keep those things. The only thing I want to point out here, because given that I still have 10 minutes, so I will get a bit of a chance to talk about the complexity as well. So otherwise, Aurobindo will kill me. So, only thing I want to point out, I can have initial state, right? I'll just do quasi-particle thing, and this is entanglement, this is time, and so on and so forth. So from this, all these things what I discussed, only thing you just remember that nail state, which is nothing but this 1 0 1 0 1 0 state. For that particular state, the growth of entanglement is maximum. And that we can understand from the quasi-particle picture. So that's the only information I want you to keep in your head. That's it. That's a very good point. We checked with some system, and it turns out to be the case. So we don't have a, I mean, that's a very good point. At least the type of model we looked at, it turns out that nail state giving you the maximum growth rate.
In the Hamiltonian, but your state is a spinful state, or should I assume?
No, it's a 1 0 1 0 state.
It's a spin state, right? Up, down, or
You can
something.
see it's up, down, or you can see
occupied
or
okay,
non-occupied.
The nail word is associated.
Oh, yeah. Nail is up, down, up, down.
Yeah.
I think up is one and down.
Charge density kind of.
Correct. But in principle, you can write it out as S plus S minus.
Yeah.
So X, it as X. Okay. So this is just keep in your head that nail is the quickest. Okay. Okay, good. Now, in 2-3 minutes, talk about what is complexity. Okay, again, it has many definitions and so on. The way I see it, that if you give me two normalized states, okay, and you want me the how far those two states are. The standard metric is essentially some fidelity. So calculate the overlap, and if you take the cos inverse, you will get some number. So essentially, it's a fidelity, right? And that gives you a measure of how far two normalized states are, right? I mean, right? Okay. Now, maximum distance can be pi by 2. They are orthogonal. Right? Okay. So now you can think about these two states, A and B. Here everything is less than 0. I mean, spin language, everything down. And you just flip one spin, let's say up. They are very similar, right? Just you have flip one spin. But they are orthogonal, right? Because if you take this particular measure, you will get pi by 2. Now I will play around. What I will do, I will take this, I will do a time evolution. I will get something. You can see that you have 2 to the power n number of basis states. So I will expand it in this basis. So we have a complicated guy here, right? And you have again a very complicated Pn, and which kind of time populating over all these ends, like 0, 0, 0, 1, 0, 0, and 2 to the power n possibilities you have, right? But again, if you calculate the overlap, you get again pi by 2, right? Because you have AT, BT, and now you have e to the power IHT, e to the power minus IHT, H is Hermitian, so they cancel. Finally, you get pi by 2. But if you ask me, everybody will agree that going from this state to that state must be very simple, right? Because you just need to flip one spin, or you need to just populate one more electron. On the other hand, here, all those 2 to the power n states are actually getting populated and so on and so forth. And still, I am saying these two states are orthogonal, without quantifying the fact that these two states are pretty far from each other. Well, I mean, in contrast to these two. You all are with me, right? You see the problem. So now the question is that, is there any other metric that can capture this differences? That's the question. And that's where this complexity story comes. I mean, again, one can define complexity in different ways. So one thing is very obvious here. How quickly you will, I mean, things will be bad will depend on this unitary, right? Because that's essentially crucial here. If the unitary was not there, then it's just flip one spin, you get from one to another. So that means this unitary plays an important. That's first point. Now, the way people define the complexity is that if I give you a unitary, okay, so how many two local gates is required to implement that unitary? So that usually one people define how complex is your Hamiltonian, or in this case, the unitary. So if you have this big unitary, this is one way you can do it. So basically, you need to tell me that, I mean, number of minimal decomposition is possible. Minimal, because I mean, you can always overdo it. But without that minimum number of two gates, you cannot do it. I mean, cannot represent this big unitary. So that's the story. And that will tell you that, okay, how complex is my Hamiltonian or unitary, whatever you call. And that will kind of very easily tell me that, okay, this AT and BT, they are pretty far from each other compared to this A and B. So that's the measure. Now, again, I mean, there is some formal way of defining this thing. So, okay, I don't want to spend too much time, but there is a formal way of defining what I just said. Okay. Yeah. So now, without knowing anything, so there are in this paper, I think there are also some other papers. So there are some conjecture, also some random matrix theory proof, which claims that this complexity for an unitary in general, random unitary, I guess, it grows linearly with time, okay, up to a certain time, and that certain time is essentially exponential in system size, and then it saturates, and the saturation value is also exponential in system size. So now you see, so this is kind of, I mean, there are some proof and also there are some belief that this is really what works. Now, if I tell you this picture and the entanglement entropy story which I had earlier, you see that there are some similarities, right? The entanglement also goes linearly with time, then it saturates, and so on and so forth. Now, the next question will be that can we connect these two stories? Now, one thing I want to emphasize here, that computing exact complexity is extremely non-trivial task, because even if you don't understand anything, you see there is INF. This is not infinity. I also did not know before Arvindo told me. It means infimum. Okay. So it means that you need to perform on minimization all this Yj and okay. So and there should be something else, right? All this Yj and Hj. Okay. And then the one which will give you the smallest number, that's basically your this complexity. So even though it looks like just an integral, but it involves some minimization. And this minimization over essentially all the Yj and so on. So in a nutshell, what I'm trying to tell you that if I give you some unitary, calculating the complexity, it's almost impossible task. But what people can do is that calculating some bounds. Okay. Now it turns out, it turns out that there exists some bound in terms of entanglement entropy. So this right-hand side is essentially entanglement entropy. The only difference is that there is also a sum, which is essentially entanglement entropy over all the cards. So let's say you have 10 site lattice. You can take one site 9, two sites and 8, and so on and so forth. So you take all the cuts, you sum over that, and that gives you some lower bound on this complexity. So, but you see, again, this formula is this, because we were running away from this minimization issue, which we had, yeah, which we had in this infimum calculation, right? But here also, if you look at it, it just tells you that you have some phi, which is nothing but some product state. So again, you have to, in principle, have all this or maximization over all the phi's to tell me what is the highest or tighter lower bound. Now the good thing is from this quasi-particle story, we know that nil is something which is for which the entanglement growth rate is maximum. So now that helps us to essentially make a tighter bound on the complex complexity. And what we show here is that, so basically this is my last slide in case, I know, So this rate are actually some upper bound of circuit complexity. So it just goes on and on. It will go on till some exponential in system size, and then it will saturate. But these are the nil entanglement entropy calculations, which is essentially the right-hand side of this particular equation. And it shows it saturates here, and then it goes linearly up to this point, and then it gets saturated. So you see that at least they are not that bad. So this lower bound and upper bound, they are quite close up to this particular time scale. Of course, that is linear in system size. And you have some scaling and so on. So take home message is here. The complexity goes linearly till this particular time scale.
There is a question from one of the Zoom audiences.
Yeah.
So Zainesh Sainya. So he's asking, in the entanglement entropy formula you showed, what kind of Hamiltonian is under consideration?
Integrable Hamiltonian.
Since you mentioned it is a counting problem, it seems very similar to Cardy formula for entanglement entropy in 2D conformal field theory. So
yes,
is the Hamiltonian under consideration same conformal invariant system, or perhaps some Hamiltonian that goes?
Who is asking this question?
Ainesh Sanyal.
Sorry?
Ainesh Sanyal.
Okay.
Yeah.
Okay.
So his question is, okay, is the
so
Hamiltonian?
in a nutshell, you are absolutely correct. So actually, I should show this thing. Can you hear me?
Yeah, Ainesh, you can also unmute and ask.
Yeah, please.
If there is question.
So, okay. So you see, so this is essentially the CFT result. So it grows, saturate, this. So in a nutshell, yes, most of this model has an underlying CFT, but the point is that you can, I mean, if you have some integrable Hamiltonian, it will do the job. So underlying CFT is not necessary, but initially when Pasquale and Cardy, I mean Calabrese and Cardy, they proved this thing. That time it was motivated from some CFT, underlying CFT Hamiltonian. I mean a Hamiltonian which has some underlying CFT. That's correct. It has a CFT. It has a CFT. Yeah. No, it's CFT in a low energy level. So it's a extremely low energy level. It has a. So it's cos k. So in low energy level, it's 1. Yeah. So in a low energy level, it has a CFT, but yeah. Anyway, when you talk about the CFT, essentially you talk about the ground state and the fast excited state. Yeah. So it shows the logarithmic scaling and other things. No, that's what I'm saying. No, that's what CFT. That's what I'm saying. Right? No, that's exactly I'm saying that. I'm saying that this model might sometimes it might have a CFT. For an example, CFT not essential, but initially when Calabrese Cardy did this calculation, so they were underlining Hamilton which has some CFT. That's true. Okay, so finish my talk. Just telling. Okay, yeah. So
sorry, can you hear me? I'm using a different mic.
Yeah, there is some question.
Yeah, can you hear me?
Ainesh?
Yeah, can you hear me? My mic was not working.
Yeah.
So
Okay.
you also mentioned that like if it's not, there is no underlying CFT also, you can do such a generalized calculation, is it?
Yeah, Ainesh, you are not very well audible. Is it possible to keep your mic closer and?
Yeah. Can you hear me?
Yeah, can you repeat your question?
Can you hear me now? Yeah. So you also mentioned that when there is no underlying CFT as well, it is possible to do this calculation, right?
correct.
So, but in that sense, like that would be a generalized QFT entanglement entropy calculation, right?
Right. So here the integrability plays the important role.
I see. So, but in that sense, like CFT gives you some sort of a, I mean, at the critical point, it gives you some sort of a way to match your answers, right? But if there is no underlying CFT, then like how would you know if you're
No, but the point is that you, for an example, if you take the XXZ type of model, the TV model, so it has a CFT up to V equal to 2. But this prediction works even for V greater than 2, where you don't have a gapless space. When you have a gap. So one thing you see, the CFT of all this Hamiltonian, it's essentially a ground state property. So when you go away from ground state, it does not matter because, and also the entanglement dynamics, which I'm talking about here, is actually the whole spectrum story, because I start with some high energy state. I'm now looking at the ground state and then evolving with the Hamiltonian. So the ground state sometimes may play important role, but it's not essential. So the whole spectrum is important. And you have the integrability, I mean, which is essentially dictating the whole spectrum. So yeah, so that's in a nutshell, yeah. I mean, the CFT is not essential as far as I can understand. Yeah.
Thank you. Yeah.
Okay. Yeah. So is there any other question?
Yeah, no. Yeah.
Yeah. Can you just, I just want to.
Yeah, you can close.
Can you just close it? Close it? Yeah. Yeah. Last. Oh, no, I don't want to show that. Yeah. Yeah. Just keep it. Just keep it. Yeah. Thanks. Yeah. So these are the 3 important points I wanted to make. One, even the entanglement dynamics is kind of a complicated stuff. For integrable system, you can have a semi-classical picture to understand its dynamics. Second, typically for the Hamiltonian we are interested in, it turns out the nail state, for nail state, the growth is the maximum. So if you have this complexity bound, you can take the nail state, calculate the entanglement entropy, and that will give you the maximum lower bound complexity. Given that you cannot compute complexity, that's essentially a good thing to compute, right? Because it's the lower bound, but the maximum of lower. So that's where I will like to end, and thanks for your attention, and I will be happy to discuss further.
Okay.
How do you do the operation?
Oh, that's so we just played around with different type of states and so on and so forth. So it's some numerical. So the good thing about this thing is that for type binding model, you know this thing because it's so even the density matrix, reduced density matrix is also Gaussian. So you know the correlator. Yeah, so you know the correlator, Cij, Cij. So there you kind of understand that why it works. But for other kind of system, again, it's just, we just played around and all these things. Yeah.
So I have a basic question if I can ask. Yeah. So can you hear me?
Yeah, you can go ahead. Please ask.
Yeah, so you need, I mean, to calculate this generalized Gibbs ensemble, in principle, you need all the conserved quantities, right, of the quantum integrable system. So, I mean, I was wondering if, like, it's a basic question, but is there a general procedure to calculate all?
No.
Yeah.
There is not, I mean, there is no general process for that. Of course, for free model, it is easy to check. Like for I mean, the tight binding model, it turns out that NKs are your conserved charges, and you have infinitely many of them. But for interacting integrable system, it is a quite a non-trivial task. So in a nutshell, for Bethe answers integrable system, I'm not sure whether, I mean, so it's a particular class of system which you can solve using something called Bethe answers. So for those system, it is kind of there. So there is a machinery exist to compute those charges. But in principle, it's real at all. Yeah. So in a nutshell, we only know few interacting integrable Hamiltonian where we can do all these things. That's for sure. Yeah. Interact. Yeah.
Okay. Thank you.
Yeah.
Okay.
Yeah.
How are you explaining the entanglement of quasi-particles out here?
Okay, yeah. Can you just? No. Yeah, now it's working. Yeah. So again, three things. First, so this is my space, right? At each point, one pair generates, and they start moving ballistically with V and minus. Second point, this quasi-particle pair, they only carry the entanglement. So this pair, so this and this will not carry entanglement. So
Why
only this pair will carry the entanglement.
Why specifically that pairs are carrying? Is there any proper?
No, so that one of the reasons is that these are some local Hamiltonian. So that's the simplest thing you can think of. And the other idea is that if you even want to incorporate the other pairs, the idea will be that that pair, the contribution will be much smaller because they are much heavier and so on and so forth. So, okay, so that's actually in some sense, that's a very legitimate question and a very good question. So it turns out there are certain models where you can have some nested integrability in some sense that you can have a two type of quasi-particle. So the one which is fastest moving quasi-particle, so they carry it fast, and so you see so you see a nice linear growth, and then there is another slow moving quasi-particle pair, so which, as you said, maybe something generated from here and this, they are like the second order contribution and coming and so on and so forth, and then again you see a second order linear growth and so on. So those things can happen, but here the idea is that this is the simplest thing you can think of. And that works because your Hamiltonian in some sense is kind of local. Local in the sense, not that it only have terms which are on site, but it can have a off-site. I mean, it can have nearest neighbor type of term, but it's not having a term which involves the first site here and the last site here. So it's kind of a local Hamiltonian. So that's kind of the simplest possibilities you can have. And that essentially describes this prediction pretty well in the thermodynamic limit. That's also very important.
It is happening in an isolated system, right?
Isolated system.
So how are you explain the thermalization of this particular system? I didn't get that. Like if
So,
you are
okay.
using it.
So for that again, I should go back this picture. So here, whenever I will talk about the thermalization, I will think at, even though it's an isolated system, but the system acts as its own bus. So that means I have the whole system. I have some small subsystem, as if the other part of the system is trying to thermalize the subsystem, and that's how the thermalization is happening. However, the thermalization here is not the so-called thermal thermalization. It's a GGE thermalization because it's an integrable Hamiltonian.
What is a GGE thermalization?
Oh, GGE stands for this integrable model. So you have, So you have the usual Patria type of thermalization. You have a canonical density matrix, which is e to the power minus beta h. So now in this integrable model, apart from energy, you have all these extensive conserved charges, which are infinitely many. You need to add them in your exponential with an appropriate Lagrange multiplier. So that's essentially GGE. So in that sense, it gets thermalized. Yeah. So that's why when you see the entanglement growth, you see in the long time limit, it's GGE. And that's basically the saturation. They saturate to the GGE. Yes.
That's
Yeah. Sorry.
What the charges? Is it a physical parameter?
Oh, that's a very good question. So these are the dynamical conserved charges. They not necessarily associated with something of physical quantities like momentum, or total particle. So those I'm not talking about those charges. So these are the dynamical conserved charges. As a matter of fact, sometimes people call it accidental charge, hidden charge, and so on and so forth. So
it is charge.
Okay, yeah. So okay. Conserved charge means some operator that commute with the Hamiltonian. Okay, so you have certain operator that commute with Hamiltonian. So in some words, with time evolution, it will not change. If you think the Heisenberg equation, right? dA dt, where A is operator, is commute with HA. So that's the expression, right? If something is not evolving with time, in other words, it should commute with the Hamiltonian. So that's charge. Okay, so that's just a moment. So yeah, so that's actually a good question, that whether you can associate some physical quantity with that. Sometimes you can, sometimes you can't, because in the sense that they are kind of tricky things. So that's why people call it a hidden. So that's why it's not even easy. If I give you some Hamiltonian to tell me what are the conserved charges, it's not apparent. So I can give you a nice example even for the hydrogen atom. So in hydrogen atom, this Lagrange vector, right? So it's not obvious from the Hamiltonian. If you look into the Hamiltonian, you see that there are nice L-square symmetry, LZ symmetry, SU2 symmetry, rotational symmetry, and so on. But the Lagrange vector, that symmetry, that A also commute with the Hamiltonian, it's not obvious from the Hamiltonian. That's why it took some time probably to figure out that that's also a conserved charge. So here the conserved charge is also something like that. So getting those charges are not necessarily that simple, at least for a gen. Yeah. Yes.
Restricted to the integrable system, or it can be generalized?
No. So that bound works for any system, but we looked into the integrable system because we kind of understand the entanglement dynamics for the integrable. But that bound is true for any system. That
Calculation, how the integrability is reflecting the bound calculation?
No, the bound calculation true for anything, true for any Hamiltonian. I mean. Yeah, so this is true for any unitary. But the fact of the matter is that the right-hand side you can compute using quasi-particle picture. So by the right-hand side is nothing but the entanglement over all the parts. That you can compute using quasi-particle picture. That you can do only for the integrable. That's.
And for the thermalization definition, you started with the pure state. If we start with mixed state, then what will happen?
That I don't know. So I don't know too much about. Any idea? So how you explain, if I start from some non-pure state, how all this story works? So complexity, entanglement dynamics, anything, or thermalization, anything.
Thermalization, these things can be definable in the same way. Only thing is that you have a channel, the CPTP map, when I'm starting with a density matrix instead of pure state, and it tends to some equivalent of the Gibbs ensemble kind of scenario. So at that time, you can always define the thermalization. And entanglement in a mixed state scenario, bipartite is more or less understood, but if you go to the many partite, entanglement in mixed state is very tricky. Even from information theory perspective, it's not well understood. So all these questions with respect to mixed state is very, very tricky questions.
Thank you. I think it's a time to conclude. We already had so many questions. The other questions you can ask later. Okay, I would like to thank Ranjan for accepting our offer to give a nice talk here.
Thanks.
And let us thank him. And I would like to conclude the session with the BCD's words. No, sir.
Well, thank you, Ranjan, for a brilliant talk. Very fascinating aspects in your talk about various aspects of statistical mechanics, entanglement, and symmetry, and so on. I'm sure we already had some very important questions, and I'm sure there will be continued discussions. So thank you very much. We deliberately planned the talks by Arvind and by Arvinda and by Ranjan at ICER. Likewise, we have 2 talks at IIT by faculty from ICER coming up after a few weeks. This is the reason being CAMOST is jointly hosted by the 2 institutions, and it's really very nice to work together. So sorry for the inconvenience of commuting, which is required. Ranjan and Arvinda, and we are going to have a similar situation when Sambuddha and Shudipto will travel to the IIT campus, but that is deliberate in the spirit of this, of the fact that the CAMOST is jointly hosted by the two institutions. So thank you all very much. Thank you, Sunil.
Thank you, sir. Okay, so we can conclude. No.
Yes.
Okay. Okay. Thank you. Thank you very much.
Goodbye.
Right.